Okay, so we're going to talk about system calls. This is a big deal for the fourth project, and I wanted to actually show you how Linux implements system calls because you probably want to emulate it in your own implementation. It's a pretty clever thing, actually relying on an understanding of cdecl. So again, cdecl, if you understand it, is a big boon, and if you don't understand it, then you're probably going to do things in complicated and unnecessary complicated ways, actually. So user applications have to talk to the kernel through system calls because remember, they're not allowed to do it directly. That's not entirely true anymore because you may or may not remember this from CS124, but there's right around Pentium 4 time, I think it was, people suddenly noticed that system calls were really slow. And it's because of all the things that happen. You have a privilege check. Are you allowed to enter into the kernel? And because all of our gates actually can say, this is the minimum required protection level on the caller. This is the protection level when you enter wherever you're going to. And so all these checks occur, and if you're changing privilege level, then you have to change stacks as well. And so it's a general purpose mechanism, very powerful, but what they noticed around Pentium 4 time is that system calls got really slow. And they actually, got to the point where it was really imposing a lot of performance impact when you have functions that call into the kernel a lot. And so they created a couple of new mechanisms, sysenter, sysleave, and syscall, sysread. And what you do is it's like a fast path. It's kind of like a carpool lane for getting into the kernel. So you kind of expect that you're going to be starting off in ring 3, and you're transitioning into ring 0, and you set up the stack, and it's basically just a fast path. If you're calling the appropriate target, then it just gets shunted right through by the processor, and it greatly improves the speed of system calls. And so, I say that we typically do this with a trap instruction, but now the way that Linux works and various other things, I should actually mention a little bit about this, is that when Linux is booting up, you've got like syscall API, and then you have various other APIs as well that are provided by the C standard library, which we'll talk about in a little bit. But when the system is booting up, it will actually probe the processor using the CPU ID instruction to see, do you support this thing? Do you support that thing? Do you support the other thing? And if it supports sysenter, it'll actually patch the system call code to use sysenter instead of using int80 because it's faster. And if it supports syscall, then it'll patch the system call code in the library with the the syscall operation instead of using int80. So it actually the kernel will update the standard library to make sure that the most optimal mechanism is used, which is pretty clever. And so we're going to talk about the trap instruction because that's the general purpose way of doing it. But just keep in the back of your mind that there's this other way of getting into the kernel that's more specialized and more streamlined. And that's probably the one that's used by 99% of system calls by now. So eventually I'll need to update this stuff. That reminds me, I have another thing I want to talk about. So maybe at the end of the lecture, if we have some extra time, I'll bring up this other topic. So yeah, the kernel registers a handler for a specific trap. This is always going to be there, even if you have your fast path stuff, because you have programs that are compiled on a different platform, and you want to make sure that you still support the general mechanism as well. So int80 for Linux system calls, obviously those are hexadecimal values, so that's going to be 128. 2E for Windows and 30 for Pintos. So if you go through Pintos and you see that you have an int30 handler, that's what that is for. In fact, that's what you'll see. Okay. Now, of course, there's not an easy way of passing arguments to system calls because you switch stacks, and there is actually a mechanism on IA32 for looking up stuff off the user stack. I mean, the user stack location is stored on the kernel stack, so you could just follow it and look at it, but nobody really does that. So typically we pass things in registers, and because you pass things in registers, you have a limited number of arguments. One of the arguments has to be which system call do you want to invoke. And the return value also goes back into EAX, which is actually very similar to cdecl, so that's perfectly fine. So Linux and Windows use EAX to specify the operation. There's a number of values you can use in syscall.h, which specify the numbers, and of course they're not always the same from platform to platform. You're allowed to pick whatever you want because you expect people will use the APIs, the C standard API or the Unix standard API, not the actual system call numbers. Okay, so yeah, there's a few constraints. One is that the system call arguments can't be wider than the registers. Typically, this isn't an issue. Okay, if you have things that are wider, you can just pass a pointer to it, which is how most of these things work. And you also have another interesting thing, that if you need more arguments than you have registers, then you can do various things, like create a separate structure to hold some values, and then you pass a pointer to the structure. So you can see large arguments split across multiple registers. Just point to them. That's another option. I have to mention that Unix has a very simple API in general, and so most of the time you either have values that fit within a single register, or you just pass a pointer to a struct. Windows is very different and again, not many of you have done Windows programming, but a lot of times the system calls take data structures, and the first value in the data structure is the size of the data structure. That's how they tell which version of the data structure you're using. So Windows sort of picks a very different approach from Unix in passing arguments into the kernel. So you can imagine that Windows system call mechanism is a little bit different because of that. Okay, so the OS exposes system calls via standard library, which is good. Okay, one of the reasons why we don't want to create our own hand-rolled mechanism that does int 80s or syscall or whatever is that if I call the standard API, then I can move to a new platform and compile my code against that platform standard libraries, and it'll just work. And so this is the whole idea of source code portability. And so this is why you can create a program that'll run on the Mac, it'll run on Unix, and you just compile it for the different platforms. Even if the system call numbers are different, it'll just work. Okay, so that's all perfectly fine. And yeah, this library that I mentioned here is sort of a bit of a veneer, if you will, between the kernel and the user application. So we just have some kind of indirect mechanism so that we can write our code and we can compile it on different platforms, and the library takes care of mapping that into the kernel. Okay, so this is why we like to do this. There's very few times when you do this directly, and probably one of the few is in CS124, so that you can see how it works. Okay, so you have some functions that directly wrap system calls. So read and write are great examples. Close is a great example. Probably dupe and dupe2 are more great examples. But you can see we take 3 arguments. All of them are the size of a register, so we're perfectly happy there. And this read implementation will call directly into the kernel because it can't really do anything by itself outside of the kernel. So that's also true for write and close and a few others. Other ones are more interesting because they will call into the kernel when they need to, but they won't necessarily do it unless they really have to. So malloc is a great example. I've got this data region in my address space for the heap, and as long as I have space to satisfy an allocation request, then I just do it by myself. But at some point I may run out of space, and so there were on Unix systems, on Linux in particular, although now we do it a different way, break BRK and SBRK, which basically says where's the memory break point for the end of this data segment. And so I can move it out if I need more space for the heap, and now the kernel will say, okay, I'm giving them more space for their memory heap. So malloc would call that if it's unable to satisfy a request. And of course, if it calls sbreak and the kernel comes back and says, no, you have enough data heap, then malloc would return null to say, I can't allocate more space. You need to free some space before you do anything else. Okay, so that's an example of an API that actually uses system calls to implement things it can't do, but it only uses them when it has to. Okay, any questions on this? All right, it's pretty straightforward. Now, we already talked about the interrupt and trap handling for IA32. That was in Lecture 9. So now we're actually in, we're talking about user processes. So we have our own user stack for running our user program. We have stuff, whatever is on there. And remember, we talked a little bit about this stuff. Not so much in this class. I guess we talked about it more toward the end of CS24. But at the very top of the stack will be like our environment and then the arguments to main. And then we invoke main and we start running, and we have various stack frames for user functions that we're calling as we run. So at some point, we want to trap into the kernel because we want to read some data, or we want to printf or fprintf or something like that. And we trap into the kernel, and there's a series of things that happen. The first thing that happens is that the pointer to the user stack, since we're switching stacks, we store a pointer to the user stack onto the kernel thread stack. Okay? And one little detail about this is that the stack segment selector value will actually indicate that we're changing protection level. So the value, you can look at the value and tell whether or not you need to change stack. So that's one of the nice things about it. The kernel has various ways of doing this to make sure that everything works properly. Okay, so that's stored. Then we store the execution state. I'm sorry, I think I misspoke. I think it's the EIP that actually stores that stuff, or the CS. So one of those values says we're switching protection levels, and so that is how the processor knows whether or not there's a stack pointer that it needs to pull off of the current stack. Okay, so we store CS, EIP, and E flags, and now we're in the trap handler. Okay, and so just to continue our discussion, remember that some interrupts, specifically faults, will store an error code indicating what happens. Most of the faults store with a specific format, but the page fault is special because it wants to say, was it an instruction or was it data that caused the fault? Is it writing to read-only memory? Is it trying to execute something that's not in an execute segment? That kind of detail will be in the error code. And just to make everything consistent, operating systems typically will push a dummy value if it's an interrupt or a trap that doesn't have an error code. So from the perspective of our trap handling, we'll have a dummy error code. We don't even look at it. We don't care. It's just going to be some value picked by the operating system. Then we have the interrupt number pushed onto the stack so that we can have multiple handlers for I'm sorry, I misstated that. We can have one handler for many different interrupts. And so remember that like IA32 supports 256 different interrupts. Most of them we don't care about. Many of them we just don't even handle. And so the operating system will install a simple handler that those interrupts will invoke if those interrupts are triggered, so that we can just say, hey, we got this weird interrupt, we don't know what it is, we'll just ignore it and go on. So that's why the interrupt number is also pushed onto the stack. Then the register state is stored onto the kernel stack. So that was the user process stacks, or I'm sorry, the user programs registers, and now we can do whatever we want without worrying about disrupting the user program. Okay, so this was all the stuff we talked about in Lecture 9 of just these various things. Now let's start looking at the system call details. Okay, so the operating system is exposing the CPU and register state to the interrupt service routine. That's what ISR stands for, interrupt service routine. And so the ISR will typically have some struct as its argument, which has all these values that were pushed by the the sort of the ISR wrapper that calls into the C implementation. And so the system call handler needs to be able to see the arguments, and those were stored in the register, so it can just access those on the stack now. That's easy enough. Also, it has to be able to return a status result in EAX, but not its EAX. So all it needs to do is just modify the interrupted program's register state, and when we IRET at the end of the trap handler, it'll see its EAX has been changed, because that program context will be restored into the registers, and it'll say, oh, okay, EAX has now been changed to store the status value of the system call. Okay? So that's easy enough. Any questions about this? This is one of those things that's kind of fun, is that since we're in the kernel and the user program is actually, its machine context is stored on the stack, and we can get a pointer to it or we can modify it directly, we can actually change things so that the user program sees those changes when we return back to it. So that's one of the really neat things about this mechanism. Okay, let's see. The specific routine that handles a system call is called a system call service routine. That's not very surprising, but basically we'll have one of these service routines for each system call that we support. And typically we name them in a way that makes it really clear that it's the system call service routine for a particular syscall. So syswrite for write, sysfork for fork, sysread for read, sysclose for close, and blah, blah, blah. Okay, that makes it really easy. And that's one of the things you'll notice this week, or I should say for the next 2 weeks, is that you'll have a file full of these little sys_blah things for the various system calls you have to implement. Now, what if you have one system call and it needs to call another system call? Well, you definitely don't want to trap into the kernel. That's dumb. That's way too much overhead for invoking the other operation. So you just call sys_whatever to go ahead and perform the operation. So that's kind of a nice thing if you need to build up some system call and you need to use various other operations. How are these things dispatched? Well, the same way that a lot of things are dispatched in both the CPU and in the kernel, we have an array, and the array is full of function pointers. The array will be the size of the number of system calls we allow, and each entry in that array will simply be the pointer, the function pointer to the system call service routine. Okay? And so what we do in the system call handler is we just use the system call number to index into that array, and then we just call the appropriate service routine to handle the operation. It's a really simple mechanism. Of course, we also need to make sure that it is a valid system call. Again, you'll notice some of these things if you look at the Linux system call implementation, which we'll take a very brief look through. But you will have some system calls, I should say some numbers that don't correspond to a valid system call. So you just put it in a special hook to a system call handler or system call service routine that says, I'm not a system call, and that's all it does. So it just sets EAX to eNoSys, and then the user program will see, oh, okay, I tried to call something that wasn't valid. Okay, so that's how you handle gaps within the system call numbers. Okay, so one of the things you do is check that it's below the max system call ID, and that was the other thing. I'm not a system call handler. Okay, so here's the way that the Linux system call handler works. This is basically the interrupt service routine. There's a lot of other stuff I'm leaving out because remember, system calls are a great point to perform context switches. So if we're doing something that's slow, we probably want to do a context switch. There's a few other things that are saved and restored and handled as well. So we're kind of ignoring all of that stuff. But the save registers onto stack is going to save the user process context. Okay? But it'll still be in the registers, so when we look at EAX, it's still whatever the user process passed in. So we just basically look at it and say, is it above or equal to the number of system calls? If it is, then we need to go ahead and tell the user program, hey, this is really bad. Notice how we access it. We say minus eNoSys, and then we say 24 ESP. Well, that happens to be the position of EAX on the kernel stack. I should say the user process's value for EAX on the kernel stack. Okay? So that's kind of gross. You kind of wish that they would do this in some better way, but that's how the kernel is written. Those wily kernel programmers. And then you return from the system call so that they see that they tried to call something that's invalid. Otherwise, you jump down to no bad sys, and you actually dispatch to the system call service routine. Okay? So we have syscall table, that is the start of the array of system call function pointers. And remember that pointers are 4 bytes on IA32, we're still in 32-bit land. And so we use EAX to index into that. We just multiply it by 4 to call the appropriate function in the system call table. Okay? Now, that'll run, and then it returns, and it follows cdecl. So the return value is in EAX, and so we just squirrel that away into the appropriate location on the kernel stack for overwriting the user process's machine context, and then we return. Okay? And like I said, ret from syscall will do things like saying, hey, do I need to do a scheduled process switch? If I do, then go ahead and do that. Otherwise, if we go right back to the kernel, then, right back to the user program, which we will eventually, then the user process's context will be restored off the kernel stack. They'll see the change to EAX, and they'll know whether or not their system call succeeded. Okay, any questions? Pretty straightforward. Now, there's an interesting thing. This system call table is full of C functions, right? They're all function pointers to C functions, and so we need to somehow figure out how to pass our arguments So those C functions. We know that the return value is coming back in EAX, so that part is perfectly fine. But we basically get to follow cdecl, and we can leverage cdecl to make this really simple. So we have some system calls that require no arguments. Okay. That's a bit of a misnomer that fork doesn't require any arguments. Fork actually needs to know all of the process's registers so that when it sets up a new process, the initial register context will be the same register values as the old one. mmap requires up to 6 arguments to specify the memory mapping change that you want to perform. And, of course, these things are passed in specific registers. And the way that we do this is EAX is the system call number, like we said before. EBX will be the first argument. ECX will be the second argument. EDX will be the third argument. ESI, EDI, EBP. Okay, so we have up to 6 arguments we can pass. And these service routines are written in C, so they do expect their arguments to be on the kernel stack. And so what the system call handler does is it always pushes all the registers in a specific order. And it pushes them in the reverse order that the arguments are used to pass the arguments to the system call handlers. Now you may already be thinking cdecl, and that's exactly what you should be thinking. So the last argument is pushed first, then the next to last, and all the way up to the first argument, EBX. Okay, so they're pushed in that order. And now that we have this set up, remember that under cdecl, if a function is passed more arguments than it cares about, it ignores the remaining arguments. That's one of the reasons we love cdecl. It's kind of resilient and robust this way. So if you have a function that only cares about 3 arguments, well, it doesn't care about the fact that arg4, arg5, and arg6 were pushed on. If we have one that takes no arguments, it doesn't care about any of them. Okay? So basically, this allows us to dispatch to all our various system call service routines, regardless of the number of arguments they take. If it takes 6, that's great. If it takes 0, that's also great. We don't care. Okay? So syswrite is a great example because it takes 3. It takes, this is for write, so we take file descriptor, we take the buffer to store data into, the buffer to pull data out of, because it's write, and the number of bytes in the buffer. And so that is handled by syswrite, and that takes 3 arguments. So EBX is the file descriptor, ECX is the pointer to the buffer, and EDX is the number of bytes to read out of the buffer. Okay? And so when the system call handler dispatches, remember, all of that stuff is pushed, and then it does call and looks up the address to call in the system call table. Then basically, we have a stack set up exactly like syswrite would like to see, so it can be written in C code. So we have the return address to jump back to when call returns, and the frame for syswrite is now set up. So, push EBX or EBP, move ESP into EBP, access my arguments. They're exactly where I'd expect them to be, and I can push other things if I need to, and so forth. Okay, so this is a pretty clever mechanism relying on the convention that we have specified of cdecl, and the fact that we can actually ignore extra arguments without affecting anything. Okay, any questions? You may want to do something like this to make your life easy. I've seen a lot of really bad approaches to writing system calls because people, probably have forgotten by this point that cdecl handles this kind of thing very easily. Okay, so there's a little hint for you. Okay, the next thing to talk about. We need to check our arguments. That goes without saying, but it turns out that there's some very naughty things that user programs can try to do, and if the operating system allows it, then you're not going to have a very good operating system. The most obvious one that you have to think about is I'm passing a pointer to the kernel, and the user process is not allowed to write to all of the address space, right? It's a user process. It's running in a restricted protection level. But the kernel is allowed to access anything, and it's allowed to manipulate anything, and it's getting a pointer from a program that may be trying to be naughty. So do I need to actually check the pointers? And the answer should be obviously yes. Let's say that we have a read operation. You could do the same kind of naughty things with write. Okay, I want to read data from the file specified by this file descriptor, stored into this buffer. Sure, whatever pointer you want, and read this many bytes. So these are the things that the caller specifies. That's pretty obvious. We're all familiar with read by now. You expect that the pointer is going to be in user space, but you're not required that it be. Like, I can pass whatever pointer I want, and so it's up to the kernel to make sure that the pointer that the kernel is handed is actually a pointer that is reasonable for that user process. What if the user program were to specify a pointer to something in kernel space? Okay. And without any checks, the kernel, remember, is allowed to do whatever it wants because it's running in the highest protection level. So if you passed an address in the kernel's address space, it would read data out of that file and plop it into the kernel wherever you want. That sounds great. You know, maybe you target the root password, maybe you target other processes, maybe you target stuff in the kernel. And so like I say here, as long as the user mode program doesn't try to dereference that address and access whatever values are at that address, it won't generate any faults. And the kernel can try to do that. And if it were to just accept the address, who knows what havoc would be wreaked. Okay? I'm really curious, just as an aside, whether or not this was caught by somebody exploiting it or somebody thinking cleverly when they were designing the system. Because every time you have a situation like this, it's not necessarily that somebody exploited it before people realized that this was a problem. So it's kind of an interesting thing. But you could target critical data structures. So I create a file with the data I want to store, and then I go ahead and pass it to the kernel and say, hey, kernel, write into this part of yourself. And it would just go ahead and do it. Yes? So as far as virtual memory is concerned, I think we'll talk about it in a second. But remember that the kernel is mapped into the same address range for all processes. So, and that's really necessary because when you do a context switch, the address range that the kernel occupies is also part of the memory mapping that changes. And so the kernel needs to be at the same location in all the processes so that when it switches, it's still at the same instruction and the data is all at the same location that it needs to be in. So the kernel part, at least typically on 32-bit, 3 gigs and up is yeah, I should be careful. The 3 gigabyte boundary and up is allocated to the kernel, and the bottom 3 gigs are allocated to user processes. And so, you know, every user process starts at a specific address, 804.8000, more or less. I mean, now people actually jitter it to, for security and safety, but then you know, so user processes all start at that address. And it's a virtual address space, so that'll be mapped to different physical pages. So different user processes will occupy different physical page frames, but they all think that they're occupying the same address space as is specified by the memory mapping that the page table specifies. Does that answer your question? Okay, cool. Any other questions about that stuff? Okay, so the kernel has to be mapped at the same location. So if a user process says, oh, I know that this thing is here, then it could try to target it because it's going to be at that address for everyone, every process. Okay, yeah, so there you go. There's a picture of it all. So, important constraints. At the very least, when you get a pointer from a user program, it must point to some address in user space. It can't point to an address in the kernel. If it does, you just say that they violated you know, the memory access constraints, and you send them a signal saying you must die. Now that's one thing you could do. Another thing you could do is actually just say, hey, you know, funny jokester, that was a bad address. You could do something like that as well. So it's kind of up to the operating system to decide how they want to handle invalid pointers because they're checking these things very carefully. Okay, so a really easy thing to do is just say, is the pointer less than C0000000? Because if it's less than that, then it's in user space, and if it's that value or higher, then it's in kernel space. Okay, so that's a really easy way to check things. And that's one of the checks that you need to do in your program. But But then you still have these other interesting situations. What if you try to write to unallocated memory or read from unallocated memory? Because, like I said, the data segment, and we actually have this here in the picture, you'll see that 804, 8000, and then above that is BRK. That's the end of the data segment for the user program. So that's the top of the heap, and we can move that, but if it hasn't been moved yet, then if we have any accesses into that darker region, then that's access to an invalid address. So we need to flag that. Okay? Or what if I try to write something that's in the program text, which is usually stored read-only? Okay? So we have these things that we need to be able to handle. And again, those things would probably still cause the kernel to fault, because it doesn't matter if the kernel wants to do it. If the memory is marked as read-only, then the operating system will still generate a protection fault for that. So the kernel would see that fault. And this is the thing that's really challenging about it. The fault is generated in kernel code by kernel code trying to access an address that's invalid. So we need to somehow say, okay, this fault generated by the kernel is a problem for the user process. Or maybe it's because the kernel's got a bug in it. I know that kernels never have bugs in them, right? So, the kernel tries to access some address, and the kernel basically segfaults. Okay? Well, we need to be able to identify that it's the kernel and not the user process. Or we could have these other situations which are not errors, which I say here. Typically, we haven't talked about this yet. We won't talk about it for a couple more weeks. But there's this whole thing called demand paging, where I don't actually allocate a page to a user process's address space until it wants to use it. So the very first access to the page always generates a fault, and that's the point where it gets allocated. Okay? So that may just mean I need to do some extra work. Or I may have a situation like copy on write, where I have a page that's shared by multiple processes and they think it's read-write, but I made it read-only so that when they change it, I can go ahead and duplicate it and allow other processes to, or I should say allow a process to write to its own private copy of it. Okay? So these scenarios need to be handled as well. So you can see that I have basically two signals. I have a page fault or a protection fault. And I need to be able to figure out which of these many scenarios it is. Is it one of these valid ones? Is it a bad pointer from a user process? Is it a bug in the kernel? I think that handles it all. So anyway, you have all these scenarios you need to deal with. Okay. Now, the nice thing about Pintos, and I just mentioned this because it will specifically be a great comfort to you at this point, there is no virtual memory yet. I mean, virtual memory is set up, but it's basically an identity mapping. And so when you have a page fault, who cares? Program is dead. It's a bug. Okay. So that's the one nice thing about that. Now, the one, yeah, no, that's absolutely true for this project. So project 4, all page faults are bad. It means somebody did something naughty. Now, when you get into project 5 and you actually have virtual memory, then you have to be a lot more clever, but you'll get there. But there are all these various situations. Okay, you have memory faults generated by kernel code. That's what I mean by within the kernel. So it's generated by kernel code, which can be valid scenarios. It can be an invalid pointer passed to a system call, and it could be a kernel bug. It could be any one of those three things, and we have to identify which one it is. Okay, so we'll talk about valid scenarios in a few weeks, because this is not the week for virtual memory. Now we have to figure out the two invalid scenarios. Is it an invalid pointer, or is it a kernel bug? Okay, so this is the challenge. Linux has a great solution to this. I think it's fantastic. So we're going to talk a little bit about it. Again, you'll see this if you have the Understanding the Linux Kernel book and you want to read the system call section. There's a whole chapter on system calls that actually goes through a lot of this stuff in much more detail than we're covering. We're basically covering it at the level that I felt motivated to actually create slides for, which is kind of a high barrier. So, but I thought this was kind of neat. Basically, the thing that Linux asks, very insightful question, is how much code in the kernel actually is responsible for interacting with user space? Is it a lot? Is it a little? Well, one of the things that you'll notice if you read either Understanding the Linux Kernel or you read the Linux kernel source itself, is that the Linux kernel actually has helper functions exactly like Pintos has for Project 4. I want to read a byte out of user space. I want to write a byte to user space. Except that Linux also has, I want to read a word, the IA32 definition of a word, 2 bytes. I want to read a D word. I want to read a quad word. Okay? So Linux actually has operations exactly like that. So when a system call service routine wants to read some data from the user process's address space, it uses these helper functions. So how much code in the kernel actually interacts with user space? It's a surprisingly small amount. It's just these helper functions. So since it's small, let's keep track of all of those addresses of the instructions that interact with user space. And that is in this thing called an exception table. Now there's other information in it as well, which makes it too complicated to want to create slides to explain it. And it's not interesting enough to explain anyway. But basically, we just keep track of all the instructions. It's wild, right? All the instructions that actually touch user space. And when we have a fault generated, we can just look in our exception table. If the fault is generated by any of the instructions listed in the exception table, then the user process passed us a bad address. That's how we tell. If it's not in the exception table, then we have a bigger problem. Because it was caused, we have a fault that was generated by the kernel. And remember, we've already identified the valid scenarios. It's not that I need to map in a page, or I need to map a page into a frame. It's not that somebody's doing copy on write. I had a fault, and it wasn't any of the good situations, and it wasn't the user process's fault. So whose fault is it? There's only one person left, the kernel. So crap, right? So that's the one thing that you need to identify. Yeah. So in the fault handler, after you've checked if it's a valid scenario, then you look in the exception table. If it's in the exception table, then it's the user process's fault. If it's not in the exception table, then it's the kernel's fault. Okay? Again, this happens. If it's, yeah, this is great, right? Now you have a choice again. The kernel just seg-faulted or did something really naughty. You could bring down the entire system. But remember, the kernel is in a kernel thread, and that kernel thread corresponds to user process. So what I could do is say, you know what? I did something really bad, and instead of bringing down the entire system, I'm just going to kill this process and switch to a different kernel thread. So that is called a kernel oops. Okay? And it is kind of a big oops, because you're basically saying, yeah, I made a mistake, and this process is going to get it because I did something bad. Okay? But at least the operating system stays up for however long. If it's starting to be unstable anyway, then you're really sad. Now, you can imagine if you have a situation like this that occurs in an interrupt handler. If it's the right interrupt handler, then you may have a kernel panic, and then the entire system goes down. Okay? But, so kernel oops is like a kernel panic junior. So it's like I can maybe recover, but it's not going to bring down the entire system. Here's an old kernel oops from I think it's actually from SunOS or Solaris running on a Spark. So you can see it's a 32-bit processor. It's a RISC processor, so that's why we have like tons of registers. It's like, what a world that would be to live in. But anyway, you can see that we have some humor on the part of the software engineers. Anyway, so that's just a simple example. Are there any questions about this mechanism? You do not have to do exception tables because your operating system is simple enough that if it does something naughty, it will just crash. So yeah, you don't have to worry about kernel oopses at least. But and you also, I don't think you have to do copy on write unless you really want to. I think it's one of those like really extra credit things. And so I mean, you have a much simpler mechanism to worry about. Page faults, mapping pages into frames when it's not been allocated yet, because you will have to implement demand paging. And otherwise, you have to tell the distinction between a user process passing a bad pointer or the kernel being naughty. So those are pretty straightforward. Okay, so if you don't have any questions, then I'm going to go ahead and throw this up here just to, again, pitch what we're doing next week. So we're going to talk about two topics that real operating systems care about a lot: signal handling and kernel allocators, which is a really important topic because, like I mentioned before, fragmentation is a thing that kernels have to think about, and kernels run longer than any other piece of software on your computer. So the kernel allocators are designed very carefully to try to avoid that. So very important thing to talk about. Okay, so that's what we'll talk about next week. So we're going to go through the implementation of signal handling. I know that's a shock given the lecture title. But, this is one of those more advanced, more sophisticated areas of operating systems. Some of the facilities that they offer to user applications. We'll do a quick review because, of course, we talk about this in CS124. But basically, signals are a way of exposing this exceptional control flow mechanism into user applications to rely on. And there's a lot of nuances, a lot of difficulties. You have to really know what you're doing even to use signals properly in any more than the most simplistic usage patterns. So that's something that makes it challenging. But you can register a signal handler. We have a couple of different things to talk about. One is that this is actually declaring a type. We had a discussion after one of the classes about this. SIGT here is the name of the type. And what it is it's a type that's a function pointer to a function that takes an int and returns nothing. Okay, so that's what SIGT here is. It's a little bit confusing because you're used to type def, the last thing, the last symbol being the type name, but in this case it's nestled in there in between. And then we can use that with signal to register a signal handler to handle a particular kind of signal. And there's a few other things that you can pass in. Remember, there's sig_dfl to get the default handling. Do I actually say this here? No, I don't. But you can also pass in sig_ign, so sig_ign, to tell it to ignore the signal as well. So you could ignore control C's, you could ignore seg faults, you could have really fun time making the craziest program ever. Don't do this, but you could write a fork bomb that can't be killed, and good luck. The machine will probably grind to a halt if you did something like that. This was the example that we gave in CS124. So we have two signal handlers here. One for SIGINT, which is control C, and then you also have SIGAlarm, which just prints out a little message saying hello. And the way that we have it set up is that we generate an alarm signal every second. We set up the first one in main, and then after handling each signal, we go ahead and request another alarm in second, so that basically we generate hellos for a long time. Now, you might remember that you can kill this. I can't remember what the command sequence is. I think it's control / or control M. I can't remember. But there's one of those that sends a sig_quit instead of a sig_int. And the default sig_quit handler is to terminate as well. So it is possible to kill this. And you could always send it a sig_kill if you really wanted to terminate it. But this was the idea. Now, there's also sig_action, which is far more interesting, because you'll notice that you can specify all of this interesting stuff in the sig_action struct, which I'm not going to show you because it's kind of beside the story today, but you can certainly use man to look up all the details. So you can either have a handler or you can have this sig_act thing. And notice that sig_act takes a signal number, sig_info, which describes details of the signal that occurred, and then this fun ctxt thing. What is the ctxt thing? So you have various details here. The ctxt, I'll just say context. This is why we say machine context so much, but this actually points to the register state of the interrupted part of our user process. So that contains all the registers. It contains a few other details. It includes the instruction pointer, and it includes the stack pointer and things like that. So we can actually modify that stuff and modify what will happen in our process when we return back from our signal handler. And this is very important if you want to implement a user space threading library, for example. Remember that this is actually exactly how Lab 7 works in CS124. We use this to implement a forced context switch from one user thread to another user thread. Okay, then there were these bit vectors, which we talk about rather significantly in CS24. You have a pending bit vector, which just says a signal of this type is pending delivery. And remember that we only have one bit for each pending signal, so if we have multiple instances of a signal occurring before I go ahead and receive them, then I'm only going to see one signal of that type delivered. So I can't use this to tell how many things happen. I can just use it to tell at least one instance of this kind of thing happened. The block bit vector is helpful because it makes sure that when a signal is being delivered of a particular type, it can't be delivered more than once, overlapping or concurrently. So like I say here, you can have a signal that's blocked and pending. When you deliver a signal, it automatically becomes blocked until the signal handler returns, and then it's automatically unblocked again. And so what you end up with is something that looks very similar to how hardware interrupts work. Because remember, hardware interrupts have to be acknowledged before you'll get another interrupt of that type, which is very similar to the blocked bit vector. And the pending bit vector is very similar to if you have interrupts disabled and then you decide to re-enable them and then suddenly you start getting interrupts. Okay, so similar mechanism, very similar to what we have in the hardware level. Now, are there any questions about signals at this point? Because we're going to start getting into all the nuances of how this works. Okay. It's pretty straightforward. I think you would all agree. So the real question I wanted to look at today is how does the kernel actually provide signal handling to user processes? And there's a number of questions to explore. One is, when do we actually deliver these signals? Because you could have a situation where the process is running, or it might be ready, or it might be blocked at any of these times when a signal is delivered. Remember, one process can send another process a signal, or the kernel can send a process a signal, and so forth. If I have multiple signals pending, how do I handle that situation? So how do I make sure that there's, all of these things are dispatched in a reasonable way? And of course, there's a lot of other questions that we'll explore as well as we go through this, but there's one area we exclude sort of intentionally, which is how this works in the context of multi-threading. Because if you have kernel multi-threading support, it turns out that in POSIX you can actually say, I don't want this thread to receive any signals. And that way, that thread will never actually run a signal handler. So you can basically set it up so that one thread only ever handles signals or whatever. You can actually have different threads handle different kinds of signals as well, if you'd like to do that. So it's kind of an interesting detail that you can do with multi-threading. Now, if you have something like a kill, sig child, you can see that the process that is going to receive a signal isn't always necessarily the one that's running when the signal is delivered to the process or generated to send to the process. So the kernel makes a distinction between generating the signal and delivering it. And generation is basically about updating the data structures of that process to say there is now a signal that's going to be delivered to that process. And delivery is about the kernel making sure that that signal is actually delivered to the process, perhaps by running a user mode signal handler, maybe by terminating the process or suspending it or whatever the signal's response requires. And there may be a lot of time between those two steps. Now, we talked about pending and blocked already, which you can always use to tell if a signal is ready to be delivered. For example, sig kill might be recorded this way, sig stop or sig conf might be handled that way. But you have a couple of other details as well. You can see you have a linked list of signals which are ready to be delivered. That's under signals, and you can see it's just a sequence of sig info objects. And then you also have sig action. So what do I do based on each signal? Remember, each signal has a number associated with it, and that's just an index into this array, and the entry in the array says, this is how you handle that signal. Okay? And there's a lot of other details that can be stored there as well, besides just what to do, because you can have some signals block the delivery of other signals while they're being handled. You can have some signals be delivered at a higher priority than other signals. All of that stuff can be configured through the sig action call. So all of that stuff has to be squirreled away so that the kernel can use it when it's delivering signals. So there's a specific function that's invoked, and it actually is specific in the name, it turns out, that goes ahead and updates a particular process's details to say this signal is now being delivered. And it is surprisingly sophisticated for what needs to be done, because you may already have a pending signal of that type, and if it happens to be a non-real-time signal, then if it's already in the queue, then it's not recorded again, because we just need to record that there's one instance of that type. There are special signals that can actually be recorded, and it'll make sure that every instance of that signal will be delivered. We call them real-time signals, but most signals are not real-time signals, so there's sort of a special subclass of those. So that's one thing. If the process is already ignoring that signal type, then don't even update the data structure, so you can see that that will occur. Obviously, there's certain ones that can't be ignored, like sig kill, so that would update the process's state anyway. But if the process is already ignoring the signal, then it just goes ahead and doesn't do anything. Okay, then these things all occur just as we would expect. One of the interesting things, I'm going to probably try to talk as little as possible, but if the process is already blocked or suspended at this point and it gets a signal and it needs to respond to it, then now we say it's actually not blocked anymore, because now it should be able to run. So we go ahead and move it into the ready state because we do need it to respond to the signal. And there are a few signals that don't get added to the signal queue, which is kind of interesting. You'll notice that they tend to involve signals that modify the scheduler state of the process. So sig kill says go straight to terminate. Don't do anything else. Don't pass go. Don't collect $200. And then you have sig stop, which moves it from the scheduler as well. Even if it's ready, it moves to a suspended state. So these things can be enforced by the kernel immediately. So we don't even store them in the queue. We just go ahead and update the process's execution state. Okay, so that's generation. When you need to deliver a signal, clearly that process that's receiving the signal needs to have the CPU. Because if it doesn't have the CPU, then we can't actually do anything on its behalf. So that's the reason for that. And basically, remember that we typically have scheduled process switches. So toward the end of doing whatever we are in the kernel, we call the scheduler, we say who gets to go next, we pick somebody to go next, and then this extra work happens right before we end up going back to the process. We say, does it have any signals that are pending that need to be delivered? If so, they're handled. If not, then we can just skip that part and go back to the user process. And there's two ways that they can be handled. One is the kernel handles it for us. So we either have a default action or we ignore it. That's easy enough. Or we have a user mode handler that has to be invoked to handle the signal. So the real process ends up looking a lot more like this. Okay, so we have this basic loop in here which says, do we have a pending signal? Yes. And then you'll notice that kernel handled signals and user handled signals are handled a little bit differently. So if it's kernel handled, we handle as many as we can. If it's user handled, we only handle one of them. Okay, and we do this weird little thing where we step back into the user process, deal with the signal, step back into the kernel, and then step back into the user process. We'll talk about why in a second. Okay, so this is all basically what I just talked about. I want to mention also that Linux 2.6 is a simple implementation of signal handling, which is kind of funny because they modified it quite significantly going forward. They even introduced this thing where you can open a file descriptor to receive signals on if you don't want to use the default signal delivery mechanism. So you can just create a, it's called signal FD. You call that, you create a file descriptor, and the kernel will send you signals on this file descriptor instead so that you can handle them whenever you want, which is kind of an unusual thing. But so this is a little bit outdated, but it's very straightforward to understand. This is how I would do it if I were implementing this in a kernel. Okay, delivery challenges. So yeah, first of all, we have the signal handler being, doing its thing and then jumping back into the kernel. Why do we do that? Well, because we had a user process context that was interrupted by the signal being delivered, and we need to restore that. So that's why we have to jump back into the kernel. We need to ask the kernel to do that for us. Also, signals on preemptible kernels need to be able to interrupt system calls. So you're in your read operation, you're in your write operation, the process is blocked or whatever. You need to be able to interrupt that. So the signal delivery mechanism needs to be able to interrupt a system call. What complicates that even more is that signal handlers can actually make system calls as well. So I made a system call, I'm blocked, and then a signal goes off, and in my signal handler, I go ahead and try to run some operations. So that is another thing that complicates this mechanism. And then probably the weirdest thing is that you can actually long jump out of the signal handler back into the user process, which you might say to yourself, how in the world does that affect this whole picture? Okay, so these are pretty significant challenges to deal with. So just talking about how Linux 2.6 does it, we have a loop like I have here in our little flow diagram, and it looks for pending signals to handle. You'll notice that some signals, funnily enough, cancel each other. So if you have a stop and then a continue, both in your pending queue, they basically annihilate each other, and you don't even have to do anything. Because if stop moves you into the suspended queue and continue moves you back into the ready queue, why do anything? Just go ahead and consume them. You'll have various other things that can happen as well. If there's no more pending signals, then the kernel returns to user process. And of course, if a pending signal is found, it's removed from the pending queue. This is kind of important that you'll notice the signal is removed from the pending queue right at the beginning of this mechanism. That becomes important later on, so I just want to make sure that I point that out. It's possible that the signal is being ignored. Now, I couldn't think of exactly what situation might cause this, but remember that signal delivery, or I should say signal generation, can have ignored signals discarded at that point. Signal delivery can also look at ignored signals, so I don't know what would cause a signal to be ignored after it's been generated already, but I suppose a signal handler could ignore another signal, and so you might have that situation that causes it. Okay, so then we see, do we need to take the default action? Now you'll notice, look at the default actions here. We have terminate, dump, ignore, stop, and continue. These are the default actions that Linux basically takes. And I should really say Unix because they all kind of do this. But notice that they all involve scheduling stuff. Or ignore doesn't really. We just throw the signal away. So the default actions are all actions that the kernel can take on behalf of the process without actually involving the process at all. That's kind of important, because this is the reason why the kernel can go ahead and handle them on its own. So if we've gotten through all of those steps and we can't handle, or the kernel couldn't handle it on its own, then it has to invoke the user process signal handler. And remember that this is actually the state of our stacks within doSignal. So we had the user process stack, it's got some stuff on it. We're in the kernel, so the user process's machine context has been recorded to the kernel thread. Okay, so we have all of that stuff. We have a few other details on the kernel stack because we're inside of doSignal, so that's why we have other kernel stack data at the very bottom. But this is the state of our system when a signal is being delivered. Now, running the signal handler is easy. We just go in and set the interrupted process's context to point to the signal handler, and we have the value of EIP to store because they gave us their signal handler. So we can go ahead and just stuff that into the machine context. When we return from the kernel, it'll automatically restore that information. So that part's easy. Except that the problem is, when we do that, we need to make sure we still get back to the user process wherever it was when the signal went off. So we need to make sure that we don't actually lose that information. Okay, so this is what I'm talking about right here. So the challenge is we need to set up a second context for the signal handler to use, and then we can preserve our process's machine context. The other thing that's interesting, another challenge, is that when we return from the kernel, remember that all of this stuff on the kernel thread gets thrown away. As we unwind from our system call or entering into the kernel, we have to make sure that we consume these details on the kernel stack. So hopefully this information and the previous thing indicate the solution, what the solution will look like. We just go ahead and create a new machine context, or we save I should really say we save the old machine context on the user process stack, because that'll be around. Okay. So we copy the CPU context of the process before it was interrupted onto the stack. A few other details as well that need to be stored. Okay, you'll notice we store blocked signals because we need to be able to restore the blocked signals when we return from the signal handler. A few other details. Yeah, so we'll talk about that in a second. Then the kernel goes ahead and modifies the machine context on the kernel stack to point to the signal handler. Okay, notice all it needs to do is set reg's EIP to the handler address, because now we want to go back to that instead of going back to the user process. And there's a few other details we need to change as well, because you'll notice we've pushed stuff onto the stack. So now we need to update our callers SS and callers ESP at the top to point to the new top of the user process stack. Okay. So of course we also need a stack frame for the signal handler, so we go ahead and push stuff. Now what's really neat about this is you'll notice that we have to push the signal number. That one's obvious. But we also need the sig info and the machine context if we are doing our advanced signal handling mechanism. Well, those things are already on the stack because we needed to save them anyway. So we can just put pointers to those things into the sig action handler frame, the arguments, and then it can access that stuff. Okay, let me see if there was anything else I wanted to say about that. So this is how signal handlers are actually able to modify the process machine context in the signal handler, and then when it's returned, it all gets restored by the kernel. It's pretty clever. Okay, last thing to do. The signal handler at the end will ret. We need to return, and we need to go somewhere. We need to go back to whatever was interrupted on the process. Well, the problem is we need to restore the machine context. The kernel is really the one that's capable of doing that effectively. So we need to do a little bit of fix-up. There happens to be a system call, which you probably didn't know about, called sigreturn. Sigreturn is basically the thing that goes back into the kernel to handle the fix-up after a signal handler so that we can go back to the interrupted process. It's a system call, so you can see we basically have this little bit of code that has to be invoked. Move sysreturn system call number into EAX and then invoke int 80 or whatever it might be that actually, if we're going to do like a sysenter or something like that. Okay, and sigreturn, all it does is it takes that machine context off of the process stack and restores it. That's all it does. Okay, so that's how we do that whole thing of we're in the kernel, we jump over into the user process to execute the user function, the system call handler. We jump back into the kernel. That's sigreturn. We jump back into the kernel, restore the user process, and then go back. Now, notice that this kind of suggests that you could use sigreturn in other ways. You could put the appropriate information on the stack invoke sigreturn and happen to jump somewhere else in your program. That might be fun. If you wanted to do things really, really wild things like that. Generally, though, people don't even know that this occurs at the end of their signal handling. Okay, now last thing that happens before the signal is delivered to the user process is we have to update the caller's ESP. I mentioned that before. And so we go ahead and return from do signal. So it goes back to its caller. We eventually end up restoring the machine context, which is now the context that points to the signal handler. So all of this stuff gets unrolled, and we end up going back to the signal handler. So now that starts to run. Okay, everybody see how that works? This is pretty cool. Now we're inside the signal handler. The interrupted process's machine context is saved safely on the user stack, maybe unsafely depending on how good the code is. And when we return from the signal handler, the kernel steps in, returns, restores the interrupted process context, and back we go to the user program. Okay, so same sequence of steps. We're all familiar with this because we talked about this last time. Sysreturn copies the process context that was interrupted back into the machine state, because now, remember, sigreturn, when it runs, will save the machine context of the signal handler. So we replace that with the interrupted process context. Then those things get reclaimed. And when the kernel returns, it will restore the interrupted process context and end up back at whatever the process was doing. Okay, does that make sense? This is the idea. Now, a few other details of this. One is that I may be blocked in a system call when a signal occurs, which means that I'm actually interrupting a system call, not just some random operation that the user process is doing. Okay, where I force a context switch, I preempt the process. Okay, typically what happens is the system will return EENTER for the system call. It was interrupted by a signal. Okay, now that's not always what it does, but that is often what it does. Because it turns out that there's a couple of calls where it can actually retry the operation. Read or write are examples of this, where it'll actually restart these if we haven't gotten to the point that important stuff is happening. So another one that's really complicated is nanosleep. Basically, if that's interrupted by a signal, then clearly I was sleeping, a signal went off, so I started running again, and so nanosleep will return EENTER and how much time it actually slept. Okay, so how do we actually achieve this? Well, it turns out that it's pretty simple, because the kernel can look at why we're in the kernel by looking earlier on the stack, on the kernel stack we're talking about here. So we would see, for example, in the interrupt number field on the kernel thread information, that the interrupt number was hex 80. We were inside of a system call. And of course, if you're inside of a system call, you can look at the register state to look at EAX and see what was the system call number that I was performing. Is it read? Is it write? Is it nanosleep? Is it something else? So it's pretty easy to tell I'm in a system call. I got interrupted by a signal. Okay, so that's all what I was saying already. So the kernel has a couple of options. Like I say here, depending on the process's configuration, and also, of course, the kernel's configuration. This obviously comes down to what the kernel wants to do. The kernel can do a couple of different things. The first one is it can just say, sorry, I'm canceling out your system call. All it needs to do is go back into the machine context of the interrupted process and write into EAX minus EENTER to say your process's system call was interrupted. Okay, so that when we return back from the kernel thread stack back to the user process, it'll say, oh, I got back EENTER, I need to retry. So that's one option. Second option is if the kernel is able to retry the operation, then it can do another thing. It can actually restore the EAX to the original system call number, back up the EIP to the int80 operation or the sysenter operation, and then return to the user process, and it'll simply retry the system call. Okay? So what we're doing is, since the kernel has total control, it just moves back to the instruction that causes the system call and causes it to occur again. Okay, so that's another interesting option that the kernel has. Again, people who are very familiar with IA32 assembly code will recognize that int80 is encoded as 2 bytes, hex CD, and then hex 80. I don't remember how sysenter is encoded or syscall, but the fix-up may be a little bit different for those instructions. Okay, so this is how we can actually interrupt or retry system calls based on signals being delivered. Okay, last detail. Signal handlers can use sig long jump. Basically what we're saying is, okay, the signal occurred, I want to terminate the signal handler, I want to jump back to some other part of my user program. Okay? We describe long jump and sig long jump as non-local go-tos. That is an accurate description. This is the state of the stacks inside the signal handler. That's why we have signal handler stack data, because that's whatever the frame is for the signal handler. And so we basically remember, I don't know if you remember set jump and long jump in great detail. Turns out that you could use long jump or sig long jump. Sig long jump happens to be strongly preferred because it has the ability to restore the block signal mask when the long jump occurs, which often is very important if you're jumping out of a signal handler. Because remember, the signal is already blocked inside the signal handler, so if you just long jump out, it won't, you'll never see another signal of that type until you unblock it. So sig long jump can take care of that for you automatically. Okay, so the question is, does performing a long jump or a sig long jump out of the signal handler break the kernel? Does it break the signal delivery mechanism? And an aspect of this that I think is valuable to consider is, well, okay, so I guess I'm not going to talk about it right yet, but I do on the next slide, I think. Why would a user process want to jump out of a signal handler? They would want to jump out of a signal handler because they don't care about restoring the old context of the process before the signal occurred. That's kind of a really important detail. If they want to jump out of a signal handler, it's because it's a big enough deal to the program that it wants to completely reset to an earlier state of the program execution. Okay? So that's going to be a really important detail. This is also why it's important to note that when a signal is delivered, we update the pending bit mask to say it has been delivered. We do that right at the beginning. So even if we jump out of the signal handler, as far as the kernel is concerned, the signal's been delivered. We don't care anymore. Okay? So the kernel doesn't need to do any further fix-up. Going back into the kernel from the signal handler was really only necessary on behalf of the process. The kernel was fine. It didn't care anymore. So yeah, like I say here, the kernel doesn't require the signal handler to return in order to complete the processing. The signal delivery is finished when it jumps to the user process's signal handler. Okay? The only real reason why it goes back is to restore the interrupted process's context and do a few other things. Okay? So sig long jump can take care of these things for us. Okay. So yeah, there's no state on the kernel stack, so we don't need to worry about destroying kernel stack information or anything like that. We're okay. So basically, if I long jump, or sig long jump really is what I would like to do, out of a signal handler, it doesn't have any effect on the signal delivery mechanism at all. It's kind of all on the user process at that point. Because there's no more information. The kernel's taking care of all of its work. The kernel doesn't have any state lying around that it needs to restore. It's moved it all to the user process. So it's completely on the user process if it needs to do that kind of thing. Oh, my slide number 2 didn't go up. I need to fix that. So Yeah, why would a process long jump out of a signal handler? Remember that somewhere there will be a jump buff, or if they're writing a good program, it'll be a sig jump buff because they want to make sure that they're doing a sig long jump out of the signal handler. So that'll be a jump buffer that is in an active stack frame. And remember, that was a really key detail. It has to be within an active stack frame. And that'll record the CPU state at that earlier point on the stack. So what we're saying is we don't care about anything after it. We don't care about the interrupted processes context. We don't care about the stack, the signal handler's context. So we're saying we don't want to restore any of that stuff, so we just throw it all away with the long jump. We're perfectly fine with that. Okay. So not only do we not invoke sysreturn, we don't care about invoking sysreturn because we don't want to restore that state. We want to restore the jump buffer state. So that's why it's okay to ignore that step of the process. Okay? So let me just ask, because that's actually all that I wanted to talk about this, which is probably good that it went short because I don't know if my voice will last. But does anybody have any questions about this mechanism? It is pretty clever, pretty well designed. So this is basically how signals are delivered in operating system kernels and how we can do all of these clever things and support all of these clever things without actually messing up the kernel and with managing the various machine contexts that are in flight during this process. So, all right, next time, hopefully, if I don't lose my voice, sometimes when I try to lecture when I'm sick, I lose my voice, and then you guys get like a week off because I can't talk. But what we're going to start talking about next time is actually kernel allocators. We'll have 2 lectures on kernel allocators because there's a variety of really interesting approaches that are used for managing memory inside the kernel. So we'll talk about that next time.